So, for like the last 40 years, our entire digital world has basically operated like a vintage jukebox.
Oh, jukebox. Yeah, that's a really good way to put it.
Right, because, the user, you walk up to the machine, you press a highly specific combination of buttons, and the computer just mechanically retrieves a pre-recorded track.
Exactly. And it plays it back perfectly.
Yeah, exactly the same way every single time. It's perfectly predictable, it's highly structured, and it entirely relies on, humans having written the music beforehand.
Right. The data has to already be there.
But overnight, it feels like that jukebox has just been hauled out of the building, and in its place, we've basically hired a live jazz band.
Yeah, that is exactly the shift we're living through right now. I mean, you don't just press a button for a pre-recorded song anymore.
Right.
You give the band a vibe, right? Uh, Mood, a messy and unstructured context, and they just improvise a completely unique piece of music right on the spot, reacting in real time to the room.
It's wild. Welcome to today's deep dive, everyone. If you are tuning in to us across the internet today, we are thrilled to have you with us.
Absolutely. Thanks for joining us.
Our mission for this program is to analyze a really defining piece of writing from March 2026. It's a blog post by Jensen Huang, and it's titled AI is a Five-Layer Cake.
It's a fascinating read. Really breaks down the physical reality of all this.
It really does, because we are going to explore this massive paradigm shift. We want to understand why artificial intelligence has fundamentally graduated from being, just a clever app on your phone to becoming this enormous, heavy, global physical infrastructure project.
Which is a huge mental leap for a lot of people.
Okay, let's unpack this. Traditional computing was all about retrieval, right? You stored data in these rigid SQL tables and you just asked the computer to fetch it. But as this text points out, AI doesn't fetch, it manufactures.
Precisely. It manufactures intelligence. Because AI handles unstructured data. I mean, it takes in the messy reality of human existence. Spoken word, raw video, context, intent, and it actually generates intelligence in real time.
Because it's literally making it up. Well, not making it up, but creating it on the fly.
Yeah, every single response is newly created right then and there. And because of that, the entire foundation of global computing had to be completely reinvented. You just can't run a live jazz band on the mechanics of a jukebox.
Which perfectly brings us to the core thesis of our source material today. When you look at AI from an industrial perspective, it is not just software, it's a vertical stack.
A five-layer cake, as the author calls it.
Right, the five-layer cake. And because we are moving from retrieving data to manufacturing intelligence, we actually have to start at the absolute bottom. We have to look at the hard physical limits of reality.
And that means looking at the first layer of this cake, which is energy.
Energy, just raw power.
Yeah, there is no magic here.
Mm.
People talking about the cloud like it's this weightless, invisible thing.
Right, floating up in the sky somewhere.
Exactly. But there is no invisible cloud. The text establishes that every single token an AI produces, like every word in a chat, every pixel in an AI image, every single prediction in a chemical simulation is the direct result of electrons moving.
It's physical work being done.
It's the result of raw electrical energy being consumed and massive amounts of heat being managed.
Yeah.
Energy is the ultimate binding constraint of the modern era.
Here's where it gets really interesting because, wait, if I'm reading this right, the text is essentially telling us we shouldn't think of AI as lines of code anymore.
No, not at all.
We should think of it as an industrial energy conversion machine.
That's exactly what it is.
But, I mean, I have to push back on that a little bit, just for the sake of argument. Technology always gets more efficient, right? Historically, chips get smaller, they draw less power, they do more.
Sure, Moore's law, basically.
Yeah. So won't we just, invent hyper-efficient, low-power chips that make this whole energy constraint completely obsolete in a few years?
I mean, it is a logical assumption, but it ignores the physics and the economics of how intelligence generation actually works. What you're describing is essentially the Jevons paradox.
That's the Jevons paradox. Wait, what's that?
So in economics, when a resource becomes more efficiently used, the cost to use it drops. And when the cost drops, demand absolutely skyrockets.
Oh, so you end up using more of it anyway.
Exactly. It leads to more overall consumption, not less. The text explains that yes, the chips do become vastly more efficient at converting electrons into calculations.
Okay.
But because the AI models are scaling up exponentially in their complexity, the total demand for power always expands. It expands to hit the absolute ceiling of whatever the electrical grid can physically provide.
Wow. So the software is really just the final expression of this massive physical energy conversion process.
Correct. You can only manufacture as much intelligence as you have electricity to burn.
Okay, that makes total sense. So sitting right on top of that raw electricity is layer 2, which is the chips.
The engines of the whole operation.
Right, the engine's designed to take that power and turn it into computation. Now, the source material uses some pretty heavy jargon here, terms like massive parallelism, high bandwidth memory, and fast interconnects.
Yeah, we hear these buzzwords all the time.
Constantly. But let's actually explain the mechanism here for you listening at home. Think of a traditional computer chip, a CPU, like a master chef in a kitchen.
Oh, I like this analogy.
Right. So the chef is brilliant. They can cook a highly complex Michelin star meal perfectly, but they can really only cook one meal at a time. They work sequentially.
One step after another.
Exactly. And for traditional software, like running a spreadsheet, this is great.
But AI workloads don't work sequentially at all. To understand just a single sentence of human speech, an AI has to calculate millions of mathematical probabilities simultaneously through these massive complex matrices.
Right. So an AI chip, a GPU, is not a master chef. It's like a stadium filled with 50,000 prep cooks.
50,000 prep cooks. That's a lot of cooks.
Yeah. And none of them are master chefs. But they don't need to be. They just need to chop one carrot or boil one pot of water at the exact same millisecond.
Right. They're doing tiny, simple tasks all at once.
Exactly. If 50,000 prep cooks work in perfect parallel unison, you can feed an entire city in an hour. And that, fundamentally, is massive parallelism.
It's a great way to visualize it. But here is the catch, right? How do you get the raw ingredients to 50,000 cooks at the exact same millisecond without causing a massive traffic jam in the kitchen?
Oh, yeah. That'd be chaos.
Total chaos. And that is exactly where high bandwidth memory comes in. The text points out that the limitation of AI isn't usually the math calculation itself, it's the memory wall.
The memory wall.
Yeah, it's the physical bottleneck of moving data to the processor fast enough. High bandwidth memory acts like an army of ultra-fast waiters, delivering ingredients directly to each prep cook station so they never spend a single microsecond waiting around.
Oh, wow. Okay, so that's the memory. What about the fast interconnects the text mentions?
So those are the meticulous communication and synchronization systems between the kitchens.
Okay.
Because when you string tens of thousands of these chips together, they have to act as one single unified brain. If the data packets collide, or if one chip falls out of sync by even a fraction of a millisecond, the whole calculation just stalls.
It crashes the whole system.
Exactly. So the interconnects are these incredible optical and electrical highways that prevent those collisions. Progress at this second layer dictates everything. How efficiently those prep cooks work determines exactly how fast and how affordable global intelligence becomes.
That is so clear. Okay, so we have the raw electricity at layer 1, and we have the specialized engines at layer 2 running white-hot, processing data in parallel.
Very hot.
But a chip just sitting on a desk does nothing except melt, right? You have to house thousands of them, power them, and cool them. Which brings us to the middle of the cake, layers 3 and 4.
Right. Layer 3 is infrastructure. And this is where the sheer physical weight of this AI movement becomes undeniable.
Yeah, the observation in the text that completely changed my perspective was the rebranding of this infrastructure. The author explicitly states these are no longer data centers, they are AI factories.
That shift in terminology is huge.
It really is, because we are so used to the internet being lightweight. You know, a quiet, air-conditioned room full of hard drives just storing old emails and family photos.
Just sitting there waiting to be fetched.
Exactly. But these new facilities are heavy industry. They require hundreds of acres of land, and they need their own dedicated power substations. And the cooling.
Oh, the cooling is insane.
You can't just blow cold air over these new chips anymore, right? The heat density is just too high.
Exactly. Air simply lacks the thermal density to carry away the heat generated by thousands of chips operating at like 1,000 watts per square inch.
It's basically a toaster.
Yeah, thousands of them. That's why this infrastructure layer requires massive plumbing for direct-to-chip liquid cooling. You are literally building complex fluid dynamic systems right alongside the most advanced electronics on Earth.
It's staggering. If we look at this transition, we are building gigawatt-scale power routing facilities that just happen to do math.
If we connect this to the bigger picture, you can see exactly why the author calls it a factory.
Right.
A traditional 20th century factory takes raw materials like steel and rubber, and it outputs a physical car. A 21st century AI factory takes raw electricity and data, and it outputs intelligence.
It manufactures it.
Exactly. And that manufactured intelligence is housed in layer 4, the models.
Ah, the brains of the operation. This is where the raw compute is organized into something that actually, understands the world.
Precisely. And what the text points out, and this is crucial, is that the public conversation is entirely too focused on language.
Yeah, we just think of AI as text chatbots.
Right, like writing emails or essays.
Yeah.
But the models are rapidly moving way beyond human language. They are learning the fundamental languages of the physical world itself.
Like what?
The source discusses things like protein AI, chemical AI, and advanced physical simulation. The models are actually learning the foundational rules of biology, chemistry, and physics.
Okay, I really want you listening right now to pause and visualize what that actually means. Think about the history of human scientific discovery. It's painstakingly slow.
Decades.
Right. A team of scientists might spend 10 years in a physical laboratory mixing compounds, testing material strength, failing, taking notes, and trying again.
It's trial and error.
Now, imagine a machine that has internalized the fundamental laws of molecular dynamics. It can simulate millions of those chemical reactions or protein folding combinations in a matter of seconds.
It completely upends the timeline of human discovery. You're replacing physical trial and error with digital simulation at just an unprecedented scale.
It changes the speed limit of innovation entirely.
It really does.
But, a brilliant model sitting on a server still doesn't change the economy until someone actually uses it. Which leads us to the top layer, layer 5, the applications.
Yes, the very top of the cake. This is where humans actually interact with this multi-trillion-dollar infrastructure build-out.
Right.
Layer 5 includes platforms for autonomous drug discovery, complex legal and coding co-pilots, self-driving cars, and humanoid robots.
Which seems so different, but they aren't.
Exactly. The text makes a really elegant conceptual point here. A self-driving car is just an AI application embodied in a four-wheeled machine.
Yeah.
A humanoid robot is an AI application embodied in a bipedal chassis. They rely on the exact same 5-layer stack as a piece of software analyzing a legal contract.
So what does this all mean? The text outlines this fundamental economic rule that drives this entire ecosystem.
Yeah.
Gravity.
Gravity.
Every single successful application at the top layer pulls demand down through all the layers beneath it.
Exactly. Let's trace it. A highly successful AI coding assistant requires more advanced reasoning models at layer 4.
Which requires a larger AI factory at layer 3.
Which has to be filled with more specialized chips at layer 2.
Which pulls an incredible amount of new energy demand all the way down to the local power plant at layer 1.
The demand just cascades downward. Every time someone uses an app, a power plant somewhere has to burn a little more fuel.
And this demand cascade completely flips our expectation of how AI is impacting the labor market.
Oh, this is one of the most surprising takeaways.
Right. For years, the panic has been all about white-collar job replacement, that AI is going to displace coders and writers and analysts.
But the source points out that because this is the largest physical infrastructure build-out in human history, it's actually creating a desperate, insatiable need for the physical trades.
It's a massive blue-collar boom. You cannot build a liquid-cooled AI factory with Python code.
No, you definitely cannot.
Exactly. These factories need commercial plumbers and pipe fitters to build the cooling loops. They need high-voltage electricians to wire the substations. They need steelworkers, concrete pourers, and advanced HVAC technicians.
We are witnessing a trillion-dollar capital rotation back into the physical world.
Yeah. You do not need a PhD in computer science to ride this economic wave.
It is a profound shift in the workforce. But, it is also shifting the knowledge economy in ways that require a deeper look. The text uses this great example of a radiologist to explain how AI changes highly skilled labor.
And we should look at this closely because it's so easy to misunderstand. The common narrative is always, well, if an AI can read an X-ray better than a human, the radiologist is out of a job.
Right, that's the fear.
But the source points out that the demand for radiologists is actually continuing to grow. It seems like a total contradiction, but it isn't.
No, it's actually the economic concept of induced demand.
Okay, explain that.
Think about a crowded highway, right? If you build 3 new lanes to ease the traffic, it doesn't stay empty for long.
No, it just fills up with more cars.
Exactly, because the easier commute encourages more people to drive, and the highway fills up again. So when AI takes on the routine, high-volume work of screening medical images, the throughput of the hospital skyrockets.
Right. The cost of diagnosis drops, so the hospital can process twice as many preventative scans.
And what happens when you process twice as many scans?
You find more stuff, you find more complex edge cases, you find more patients who need comprehensive care plans.
Exactly. The radiologist doesn't go home. They are finally freed from the mechanical task of just staring at normal scans all day, and they're reallocated to the tasks that require genuine human judgment.
Patient communication, complex medical strategy.
Yes. The author distills this into a really powerful summary. Productivity creates capacity. Capacity creates growth.
Wow.
By removing the bottleneck of those routine tasks, the entire system expands.
It is an incredibly powerful framework, but, this brings up probably the most urgent question of this entire deep dive. If this is truly the largest and most expensive infrastructure build-out in human history, why is the switch flipping right now?
It's a great question.
Why, specifically in the last 12 to 18 months, has this kicked into such hyperdrive?
The source material addresses this directly. It identifies a critical threshold that was recently crossed regarding model reliability.
Okay.
Because for years, language models were fascinating toys, but they suffered heavily from hallucinations.
Yeah.
They would just confidently invent facts.
Yeah, you couldn't trust them with anything important. But the text notes that reasoning has dramatically improved and grounding has finally been achieved.
Yes, grounding is key.
And because these models are finally grounded in factual reality, we've crossed the threshold from, fun creative writing tool to enterprise software you can actually trust to manage a logistics pipeline or write production code.
They are finally generating massive, measurable economic value.
Exactly.
What's fascinating here is it's the specific catalyst the author points out for this explosion.
Right, because you might assume that a shift this massive is being driven entirely by highly guarded proprietary corporate secrets.
Right, companies locking their AI in a vault and charging a fortune for it.
But the text highlights the completely disruptive role of open source models. It specifically points to a model called DeepSeek R1 as a prime example of this.
Which feels like the ultimate economic paradox, if you think about it.
Right, because we literally just spent 20 minutes discussing how it costs billions of dollars in power, chips, and factories to train these reasoning models.
Billion.
Why on earth would anyone spend billions of dollars to create frontier-level intelligence and then just give the blueprint away for free? Doesn't that just destroy the whole business model?
You would think so, right. But it is actually a brilliant, almost aggressive strategic maneuver. Giving away the most expensive intellectual property in history for free acts as a Trojan horse.
A Trojan horse.
Yes, it creates a massive demand vacuum.
Okay, wait, explain how that vacuum works.
Well, if a highly capable open source model reaches the frontier of reasoning and it's made available for free, it is instantly adopted by researchers, startups, and enterprise companies globally.
Because it's free.
Exactly. It puts advanced AI into the hands of millions of developers who previously couldn't afford the API costs of those proprietary models.
And what happens when millions of developers suddenly have free access to a powerful reasoning engine? They start building applications at layer 5.
Yes.
Millions of new agents, co-pilots, and automated systems.
Exactly. It triggers an absolute explosion of activity at the application layer. And remember, our economic rule of gravity.
Every successful application pulls demand down through the stack.
Yes. If millions of free models are deployed into the world, they all require inference compute. They all need to run on something.
So by making the software free, you essentially force the world to buy the hardware.
That's the trick.
You are giving away the recipe for free because you are in the business of selling the ovens and the electricity required to bake the cake.
Precisely. The open source movement accelerates global adoption, which in turn demands more data centers, more chips, and ultimately more energy.
It's wild.
Open source is essentially pouring rocket fuel on the physical infrastructure build-out. It forces a global arms race where every nation and enterprise realizes they have to build their own AI factories or just be left behind.
It is a continuous, self-reinforcing loop of demand. Intelligence gets cheaper to access, so more people integrate it into their businesses.
Which requires more physical infrastructure.
Which requires more raw energy. And the text makes it incredibly clear. We are still in the absolute early innings of this transition.
Very early.
The power substations haven't all been built yet. The liquid-cooled factories are still under construction. The blue-collar workforce is still being mobilized. But the trajectory is permanently set.
It is a fundamental industrial transformation,
Yeah.
one that is going to reshape how human economies grow for the next century.
Unbelievable. So, as we wrap up today's deep dive, let's just take a quick moment to review exactly what we've unpacked for you.
Yeah, it's a lot to take in.
It is. We took a hard look at Jensen Huang's five-layer cake of AI infrastructure and how we are moving from a digital world of data retrieval to a heavy physical world of intelligence manufacturing.
Starting at the bottom.
Right. It starts at layer one. Energy, the absolute physical constraint of electrons and heat. Sitting on top is layer two. Chips, those highly parallel prep-cook engines converting that energy into computation.
Then comes layer 3, infrastructure.
Yes, the massive, liquid-cooled, heavy industry AI factories required to house those engines. And that physical base supports layer 4. Models the brains that are actually learning to simulate the foundational rules of chemistry, biology, and physics.
And finally, layer 5, applications.
Where all of this physical effort is translated into real-world tools that pull economic demand back down through the entire stack. The ultimate takeaway from our source today is that AI is no longer just a piece of software. It is the new, essential physical infrastructure of the modern world.
It truly is. And, this raises an important question, something for you to mull over after we sign off today.
Let's hear it.
The text firmly establishes that energy is the ultimate foundation of this entire stack. It sets the absolute hard ceiling on how much intelligence a system or even a nation can produce.
Right.
So what does the future look like for communities or even entire regions of the globe that struggle to generate or distribute enough power? As intelligence becomes a manufactured commodity, will access to raw, reliable electricity become the new permanent dividing line for access to global innovation?
Wow, that is a profound and weighty thought to leave on. The physical power grid ultimately dictating the intellectual future of society. Thank you for listening. We hope you enjoyed today's content, and we will see you in our next program.